Now I can have a quadratic term again, like before, starting from this term. And that's going to be precisely the same story as we just had with the external magnetic field, because here, the external magnetic field was B cross something which depends on the electrons. Now we have MA cross something which depends on the electrons, and we have to take the square. The square means the scalar product. So we have the scalar product of that with itself, and I want to have the MAs as far out separated as possible. So I end up again in a term which now looks which then looks like this. Where is it? So I get E squared divided by 2ME. That's just this. Then I get the mu 0 divided by 4P squared. And then I have, and let's put a big parenthesis around here, I have one magnetic moment to the left, and one will eventually be to the right. And in the middle then, I get the sum of all electrons, and I get, oops, no, I should have a round parenthesis, I guess. I get very much the same expression as similar expression as I had up here, except that those terms look slightly different, because now it's not the gauge origin, but the position of the nucleus, and it's divided by this distance to the third power, which is this. I mean, it's those terms. One for the nucleus A and for nucleus B. And I sort of look now at the operator with two nuclei. So I get Ri minus Rb vector, and I do the transposed first, times Ri minus Ra, I guess now, yeah, divided by Ri minus Rb to the third power times Ri minus Ra to the third power minus, and now just the two the other way around, where I get, let's see, Rib, Ri minus Rb times Ri minus Ra, A vector, vector transposed, big parenthesis, and the denominator is the same. Don't need to write that once again. And that is called the diamagnetic spin orbit term. So it's diamagnetic nuclear spin electron orbit term, where I have two different nuclear magnetic moments. And you can see that having two different nuclear magnetic moments, that must be a contribution to these NMR spin-spin coupling constants. Because there I have two nuclear spins interacting with the electrons, so therefore two nuclear magnetic moments. So that's a contribution to the spin-spin coupling constants. Now we're missing one term, because inserting the vector potential in here and in there means the sum of both vector potentials. If I have an external magnetic field and a nuclear magnetic moment there at the same time, then I have to insert both magnetic vector potentials. I'm doing that. I had done that for the linear ones here, for one of them, and for the other one. But for the quadratic one, I'm also getting a mixed term now. Because the A here this A and that A which we replace is not just one of them, but it's the sum of the two. I have both perturbations there at the same time. So I get, of course, I get AB plus AMA, but here I get AB squared, AMA squared, and I get twice the mixed term with one of this and one of those, which is very often called bilinear, because it had both terms but only linear. And that at the end then looks like, that's only just for one nucleus again. And then this looks like, I get MA, nuclear magnetic moment. Then I get lots of constants, slightly different now, E squared divided by, yeah, I get still E squared divided by 2ME, but I only get 1 mu 0 divided by 4P. And I get a sum over I, like always. But now, and I'm missing this, I guess. Now I get, let's start with the one from the magnetic field. That's the simple one. So this is the part of the vector potential from the magnetic field, and now comes the part from the magnetic moment of a nucleus, RA, divided by RA to the third power, minus the other way around with respect to transposed, so it's going to be Ri minus Rg, and then Ri minus Ra transposed divided by that distance, like this, parenthesis, and that parenthesis, dot B. And you will notice that they are sort of overcross. It's this one which goes with that, and that one which goes with it. And we actually should have had the same here, or we also have this one here, and that one with that. And this starts also with a D. Well, that up there also is a D, diamagnetic. So all the ones which are quadratic are called the diamagnetic contribution. That's the diamagnetic contribution to the shielding constant, sigma A.